All right, good afternoon. Really happy to be here at ROSCon 2025. How many of you are attending a conference, a tech conference for the first time? Oh, there's a lot of you. Okay, so let's break the ice, shall we? Can you all stand up for me? Like everyone. Like literally everyone. Like, could you stand up? All right. So there is one person who's sitting in the right, and there is one person, on the left. Could you just look at them, shake hands with them, and say, "Hey, I'm really happy to meet you today." Come on, shake hands. All right, now, yeah, thank you very much. You can sit down. Yeah, now it makes sense that now after you go out, you have familiar faces, you can speak to them, and you can share your thoughts, and that would be a great conversation. All right, so welcome to this talk on vision language action models for humanoid autonomy with perception, language, and whole body control. My name is Pranav Durai. I am the co-founder and CTO at Frontal. We are an early stage advanced humanoid robotics company from Bangalore. The holistic vision that we have is that we want humanity to thrive beyond Earth. So we do that by building humanoids for Earth's work today and for space tomorrow. A little bit about my background. I did my research fellowship from Stanford University School of Medicine, where I led a team to develop 3D organ segmentation models specifically for early detection of cancer in stage 1 and stage 2 itself using PET-CT imaging, right? And before that, I was a senior computer vision engineer at OpenCV. I worked on a lot of projects over there, so including building ADAS systems for autonomous vehicles using just stereo vision, right? And then I worked on computational pathology for cancer analysis. And then I also worked on small object detection on satellite imagery, right? And after that, I joined as a founding team member at 10x. So we built a construction autonomous robot. I was part of the computer vision and perception team over there for the robot. Right? So this is the agenda that we have for today, right? So we know a little bit about the classical ROS2 pipeline that we already have, right? And then I want to dive a little bit about the VLA model, like how there are a lot of these VLA models and the architecture within the model itself. And then the third thing is, now that you have a VLA model, I assume like 80 or 90% of all of the robotics company right now, they're running on classical robotic-based stacks. So that's already powered by ROS2. So if you want to integrate a new VLA capability within your ROS2 pipeline, how do we do that? And what are the different use cases that we can derive from that, right? So we'll have a look at that. And then what we'll do is we'll have a look at whole body control pipeline for humanoids. So how we can kind of build and split all of these modules into individual functional units, and then bring all of them together to control the whole humanoid. And in the end, we'll just quickly discuss a little bit about the future directions and how the ROS2 community can help develop this. Right? Does that sound interesting? All right, cool. All right, so we know that the classical ROS2 pipeline is very naive, right? So we have nodes that kind of talk to each other and then try to do a specific capability, right? So the first thing is you need to look to kind of do something, right? So then we have a vision node, and that actually has two main components, right? You have some perception where you actually have two-dimensional cameras. It can be a stereo vision or it can be a monocular vision that you have as part of your robot. And then you also have a little bit of recognition, right? And this is where state-of-the-art deep learning models come in, right? So now that you're capturing all of this data in real time using your perception stack, you want to be able to understand some things out of that image data that you get from the cameras or from the 3D LiDAR that you have. So you do a little bit of recognition, right? The second thing is you have a planner. So based on whatever you saw in real time, you decide to do something, right? So now you have global as well as local planners that you kind of use to do different capabilities, right? And in the end, you actually want to do that action, right? So let's say if you want to move from point A to point B, right? You decide, you plan, and then you pass that control to your motion controller over there, and then it moves the robot from point A to point B, right? So now the pros is that it's interpretable, right? So now it's laid out in this fashion over here. You can easily understand what each node does, right? But the con is that it's a manual design and it has slow coupling. The second thing is the VLA model that recently has been making a lot of waves, right? And a couple of my speakers today also spoke a little bit about VLAs and how they're helping, right? So you have three main inputs as a triplet: the vision from the camera itself, the textual input, that is the language translation that you have in terms of the instruction that you pass into the robot, and then you also have the joint action states that you use to give some instruction, right? And then you notice that there are three encoders. You have a vision encoder or the visual encoder. You have a text encoder, right? And then you also have a state encoder, right? Now these are encoders that have already seen millions of data points of all of these triplet data points that you pass as an input, right? So then what they can do is they can generate tokens out of it. Now transformer-based architectures, they thrive on tokens, right? So what you can do is after you create tokens for each, the vision, the text, and also for the state, you pass them as inputs to the LLM that you have, and these can be any pre-trained LLM that has already seen this data, right? So now you're just fine-tuning that LLM again with your specific capability, right? And in the end, you have an action decoder, and this action decoder is nothing but a diffusion transformer, which can then predict the joint states to do that specific task, right? So over here, it's open the box, right? So you have two arms in the humanoid, let's say, and then you do this multi-hand operation to go and open that box. All right. So now, how do you integrate this into your ROS2 workflow, right? So now you already have these modular nodes which are already part of your pre-existing ROS2 workflow. So you have your raw image that you capture from your perception stack, which is through the camera itself, right? And then you pass that to the vision node that you have within your system. And then what you do is you create a new node which actually has the VLA model as an policy, right? So for each of the different tasks that you can do with your VLA model, you have different policies, right? So you can segregate them based on that. And in the end, you have a control node, which is already the pre-existing control node that you had, right? And then you pass the outputs from your VLA policy node to that, and then it does your joint trajectory and goes and performs that task. The second thing is, now that we have a lot of capabilities using NVIDIA's Isaac Sim, you can kind of use that for both training and real-world validation, right? So now what you can do is you have your task input that you pass to the VLA as an input, right? And then you can see that there are synthetic scenes that we can set up within NVIDIA's Isaac Sim itself. And I think Meher also spoke a little bit about creating simulations in 3D for NVIDIA's Isaac Sim, right? So then what you can do is you can have individual NVIDIA Isaac Sim rollouts based on sensor simulation, domain randomization, and also your skill and trajectory optimization that you can do within the sim environment itself. And during this process, what you can also do is you can collect data, right? So that can include images, it can include states, the joint states, and also the actions that you have to perform that task, right? And now that you have the data, you can also mix it to add it as a feedback-based loop into your training pipeline and make your VLA better, right? So then that can be part of reinforcement learning and also imitation learning, right? So you observe something and also you learn from what you observe, right? You update your VLA now and it gets more robust for that specific capability. Then what you do is you deploy it in your robot. Now, I see a lot of these companies struggling with latency, right? So you ask a robot to do a task, and what happens is that it takes a lot of time to do that task, right? So most of the problems arise with sequential programming, right? So you say that you go from A, B, C, D in your control pipeline, and it has to follow that same A, B, C, D control mechanism to do that task, right? So the idea here is to handle latency using asynchronous topic updates and local reflex loops within your control system itself with the integration of the VLA into your pipeline, right? So then what you can see now is that you have a very high level command on the top, the language or the task goal that you give it, and then you have a async or an asynchronous node which is running your VLA model, right? So in case if you're doing an edge deployment, for example, if you have an NVIDIA Jetson device, you also have a capability to add a external GPU on that NVIDIA device using PCIe, right? So if your VLA model is really large and if you're not able to quantize it, right? So you can implement or make that VLA model run solely on the external GPU, and that would be an asynchronous node in your pipeline, right? So then what you do is you rearrange your system modules a little bit, right? So what you can see is that the VLA inference node is talking to both the skill publisher and the local reflex controller, right? So then you also have a lot of these sensors that you use in your robotic platform itself, right? You have some force feedback, you have some IMU data that is coming out of your device, and you also have some tactile sensing feedback if you're using a different type of manipulators, right? So these are like high resolution, high frequency data that is coming from your sensors in your robot, right? Now what you do is you pass that information to your motion planner and your ROS2 actions, right? Because that requires those two streams as an input, right? And then what you do is you have a reflex correction to the joints, right? Where you control a little bit of balance, slip, and also contact forces for different capabilities in your robotic platform itself. And then in the end, what you do is you pass all of that to a low-level control unit that you have within the robot, right? So this will help you to directly control the hardware joints in real time in a much faster frequency, right? The second thing is you can also do object handover in both the tool in simulation and as well as in hardware, right? So the idea is basically to split the development into two branches. So one would be in simulation. You can do different things as part of simulation itself: contact dynamics check, reachability, stability analysis, tool use sequence validation. All of these things can happen in simulation. And then what you do is you have branch B, where whatever you've done in sim, you also have a few other things that you want to focus on as part of the real world physical robot that you have. So over there, what you can do is you can fine tune your grasp, your trajectory, your visual servoing, and also you can do your detection using your IMU, tactile forces, and all of those things. And then what you do is you club those two development pipelines together in the end to do a successful handover. All right, so this is the whole body control pipeline for humanoids, right? So now if you have a VLA model that is running real time on your robot on the edge, this is how you would kind of split that into segments and control each and every individual parameter in the humanoid itself, right? So on the top you can see that the VLA has given up an output during inference. It says that, hey, pick up the bottle. Then what you do is you do task decomposition. You break that task into multiple subtasks, right? And then there is one whole body control manager which takes care of all the different DOFs that you have in your humanoid. Like for example, a humanoid might have 58 degrees of freedom in terms of DOFs, right? And then what you do is that control manager talks with a multi-priority optimizer, which can either be using a quadratic programming pipeline or using an MPC, right? And then you split this into priorities, right? So you have high priority, medium priority, and low priority based on what you want the humanoid to do, right? And then you have one joint level command manager which has access to every individual joint in your humanoid, right? So you have the upper body, so anything from the head to the torso is the upper body, and the lower body, anything from the torso to the feet is the lower body. And then the wrist is very complex because if you want to do dexterous manipulation for complex capabilities, then that would be a separate thing, right? And then in the end, you have one low-level ROS2 control component which takes this information and then talks to the actual hardware that you have in the humanoid, right? So I'll just end this off. So what are the future directions and community involvement that we require, right? So the first thing is we need to expand VLAs with more multimodal data, not just vision, text, or actions. I also want a little bit of tactile sensing and also force modalities, because we humans not just see and learn, but we also feel and learn, right? So different objects require different forces or torques to be able to interact with them, right? Second thing is we also need to be able to develop different ROS2-based benchmark capabilities in terms of metrics, so that we can test these VLA models. The third thing is we also need to talk or try to put some efforts into open source data sets to train all of these large VLA complex models. And then the last thing is we also need to collaborate with academia, right? So most of these technological universities have robotics labs. So you also have really talented students that are coming up that want to contribute to robotics, right? So it only makes sense to collaborate between academia and then the industry itself, right? All right, so that brings us to the end of my talk. Whatever I've showed you right now is going to be obsolete because Frontal is building a foundational model for whole body control, right? So we are not just relying on existing VLA models that can just memorize tasks. We are building models that can also learn new tasks on its own, right? And we're not just building foundational models, but we're also developing hardware for humanoid robots to do all of these complex tasks, right? So if you have any feedbacks, you can follow you can scan this QR code, and then you can share your thoughts. Or if you have any questions, we don't have time right now, but you can share your questions on this Google form. I'll reply to everyone that sends a response over here. But if you also want to follow Frontal's journey, you can Google my name. It's Pranav Durai, and we can connect sometime. My co-founder Mohit and I will be at ROSCon today and tomorrow. So if you want to talk, we can talk. And then we are also hiring for different roles at Frontal, right? All right, thank you very much. Have a nice conference. Take care.